we come back to so these are so called operational laws. So one of these laws we have already seen at Little's law, but this chapter provides the foundation for the closed queuing network analysis we will do in subsequent classes. Okay. So what does this word operational mean? What does an operational law mean? Something that is based on the system, understanding the operation of the system. So these are laws that you can actually measure, right, you can verify empirically. If I tell you that memoryless property, for example, it is a little bit hard to verify, right, we will see one of the laws which is actually memoryless, which is based on the memoryless property. So some laws we can observe in a system and actually experimentally measure and empirically verify that this law holds true, okay. Whereas some other laws we are based on, we base it on some sort of mathematical principles and just use that as a law, right, even though it is kind of technically hard, might be physically impossible or infeasible to actually verify those. So operational law simply, right, means that the laws derived so based on direct measurement. The actual rules are fairly straightforward. Okay, and likewise we will also use, we will measure, we will make some measurements, right. What are these measurements? These are called operational quantities. So these are based on measurements during a finite observation period. Finite observation period which will from now on use this t. Okay. So some things I can measure, number of customers arriving per unit time, right. I can measure, sit there for 2 hours at some bank or whatever and then measure the number of customers who arrived in 2 hour period, then I can say average arrival time equals, right. So that is a measurable quantity. So based on these measurable quantities we will try to cook up some laws. Okay. So right, so during time t so ai is the number of arrivals, then we measure the number of completions, right. So how many customers complete. So this is measurement of arrivals at whichever, a single queue or entry to the system or a queue within the system, likewise completions at a queue inside the system. Okay, and then I can also measure the busy time of the server, right. So now I can just know when the server is busy, when the server is not busy. Previously we had this p naught equals 1 minus rho, that is a derivation, but here I can simply monitor a system and then find out how often or what fraction of time this particular device CPU or disk drive has been busy. So this is the busy time of the server, right. So I have one server, I am looking at how many customers arrive, how many customers leave, and the fraction of time that the server, the time, the actual time, this is right. So t is the actual time and bi is also in units of time. Okay, so we know some standard rules, right. So the arrival rate for this queue, right, we will say at some, right, this is a device I, so that is where all the I subscripts come from. So there are several such devices or queues and at one particular device I making these measurements. Arrival rate to this particular device is ai by t. then the throughput, which we will call xi, is simply nothing fancy so far, just basic derivations. Then utilization, so this is the fraction of time that the server was utilized, which is simply bi by t. Okay, so these are all so now service time, right, mean service time. So when we say service time is exponential, that is not that is kind of difficult to measure, but here this is the mean service time, right. Mean service time of a customer in that spent time in this queue is what is it going to be? Busy time by completion, right. So therefore server was busy for bi time units and then there were ci completions, therefore this is the average service time. This is service time, not the queuing time, only the service time. Okay. So we will have some 4 or 5 laws. So this is a so called utilization law. As I said, by themselves the laws are trivial, but they help us in arriving at properties or performance metrics for the queuing systems itself. Okay. So the utilization of a server equals the throughput times the average service time. Sorry, yeah. Does it make sense? So the number of customers completed into the number of customers per unit time into time. So this is and this by the way is nothing but if you look at our old MM1, right, what is this? Rho equals lambda into 1 by mu, right. Wasn't that our definition? So now your lambda is nothing but your throughput, right. In any system, in an MM1 system like this, your in a given queue, number of customers should equal the number of arriving should equal the number of customers departing, right. We saw this earlier on too, that the departure is also a Poisson process with rate lambda, right. So in this case your throughput equals your arrival rate. So that is what this is, and if you really have to derive this, can we derive that? So what is ui? Is bi by t so what do we, how do I bring this to this form? Just multiply divide by ci, right. So this is ci by t into ci by t is xi, this is si. Yeah. Ci by t, that is the average number of customers finishing per unit time, right, and average service time, this is only mean average service, nothing else, right. It is not a proof, you can verify this, right. We have our MM1 system there, okay, just go there and measure for some unit of time, right, measure the time that the server is busy, number of customers arriving, number of customers finishing, and the actual utilization time. You can start with the time when the server is empty. When it is partially busy, it is kind of difficult because there is some part of the service time right from the previous. Okay. So if you really want, okay, well we have done this examples before. Okay. So u equals xs, right, that is all, you remember that, u xs. then there is this thing called forced flow. Okay. So this law will try to relate the overall system throughput to your device throughput. So I have a system of queues, packets entering, packets leaving. So I can measure the overall system throughput at the departure point. I have several queues inside the system. So I want to measure the throughput in terms of the number of packets leaving every device, right. So I am trying to connect the device throughput and the system throughput. So that is what this is trying to do. So throughput for an open system is clear, simply the number of customers finishing completion. Throughput for a closed queuing network, we have this notion of where there is one line that is connecting in to out, right. We measure the number of customers entering that link, the connection of the out to in link, there is one link there, right. From the out to in link you measure the number of average number of customers traversing that link will be called your throughput. Okay. So if I have an open queue system, this is a big black box, right, where customers enter, customers leave, right. So this is your queue network. So this is where you will measure your, we will call this X as a system throughput. Okay, this is your arrival, right, and this is your system throughput. Okay. Whereas if it is a closed queuing network, like we have seen before, so there is one special entry point, right, and then lots of things happen, but then somewhere from this system, right, I will have something. So we have to specially designate as which is the out and which is the in, okay, and then the customers that are traversing this link from the out link to the in link is technically, when we saw this in right. So for example, there is a multi-programming system, right. So when a job goes through several queues, CPU, device queues, when finally it finishes, what happens in multi-programming? It gets replaced by some other job in the ready queue, right. So that is why there is always a continuous flow of packet or jobs in the system. So the number of packets traversing this out to in link is technically called the throughput of the system. So this we will use later on. Is that understood? Right. So this is your throughput from out to in. You look at the average number of customers traversing. Okay. So then we have the so called flow assumption, right. If during time t, okay, so the number of arrivals equal of right, that is in other words, a job does not go into a system and get stuck, right. So whatever enters ultimately has to leave the system. See, that can happen when you have a finite queue, right. When you actually accept the packet, once the packet comes in, you drop the packet, then so what, so your completion is not equal to your arrivals, right. In that case, this assumption does not hold true. It has to be an assumption where whatever is accepted for service actually completes and finishes the service. It could be in partial service at some other interim queue, but it is not dropped by the system as such, right. So if this is this condition is true, then we can have some results, right. So this is your the flow balance. An example of a system where flow balance is not maintained. Have you seen I Love Lucy? One of those episodes I am referring to. Anybody? People heard of Lucille Ball? My gosh, okay. So definitely there is a huge generation gap. So you should look at so Lucille Ball. She was back in the 50s. But anyway, by the time I started watching TV, she was already that show was almost 40 years old. But still, so there she is employed as an operator that's working in a chocolate factory. Right? So her job is to this pipeline chocolate pieces go by, simply take it, wrap it, right, and then just keep it putting. So the chocolates come this way, you have to take it, wrap it, and put it back on the pipeline. So this is your jobs coming in and jobs going up. So so initially she's the pipeline, the conveyor is operated very slowly. So she's able to, right, she will casually take one and then start doing this, and then of course they start increasing the speed, and that's when it's more of a slapstick comedy than anything else. So if you can probably download this on YouTube and check for Lucille Balls. So then they start sending this bell so fast that she cannot take everything and then at the same time put it in a wrapper and send it out. So she simply eats. She keeps on eating halfway through, and that's all. That is a job where system where your flow balance assumption does not hold, because the number of chocolates coming in is not equal to the number of wrapped chocolates going out. And again, only if you see that, then you will probably, right, it's more hilarious when you see than when it's described. Okay, so this is one assumption that we make, right? Jobs leaving equals to the jobs arriving for some observation period. Okay, so now we'll have to define something called a visit time. We did visit earlier on in context of semi-Markov, similar definition here, right? So suppose each job requests device I Vi times. So where does this happen? So you have system running on the CPU, right? So even if it's simply running on the CPU, you run on the CPU once, then you get kicked out because your quantum is up. You come back to ready queue, then again you get executed at some other point in time. So you simply might request Vi times CPU will be you will ask for the CPU Vi times, right? So you will run that many times on the CPU itself, or you could run on the CPU once, then go to a disk, get processed, and come back to the CPU, and then run again and go to another disk and so on. So you have this repetition of asking for the CPU, asking for disk A, disk B, and so on, right? So over some period of time, you make a measurement that this again is an average though, right? Because it's possible that one process will request disk A twice, others might discuss or require the disk 10 times and so on. So we are sort of hiding away all that, assuming that all jobs will request each device for the same number of times, right? That is one simplification that we are looking at, okay? Which is in a real system that is not really the case, right? You will have multiple okay. So if this is so Vi is so called visit ratio. Visit ratio of device I. This is for a single class system. There are multiple, you can derive this queuing networks for also systems with multiple classes, right, where each class of traffic has different requirements. Each class of job that is running in the system has different requirements. For now this is a single class system. Okay. So then if the job flow is balanced, and let right C naught, this is CO, be the, it's sometimes convenient also to call it C0 because all the devices are numbered 1 through n. So this is the number of jobs traversed, this is basically your throughput, right. This is simply the number of jobs that is traversing your outside link, then your Ci is defined to be C0 into Vi, right, because every job requests device I Vi times, there are a total of C0 jobs that have left the system in this observation period, therefore the number of times, the number of completions, right, of device I will be simply the total number of completions into the number of times that each that particular device was requested by a given job, right. So if number of jobs finished is 5 and each job requested a disk 10 times, then the number of completions of that particular device is 50 completions. You are treating them all as independent, right. So even though the same job has come to the disk 10 times, technically speaking they are all independent completions. But then that got kind of stuck in, yeah, that is why that we are assuming that in this measurement period jobs came and jobs left, that there is nothing left behind in the system, right.
Because if you have a queues, definitely you have at least buffers.
Yeah, so let us say that this is that device queue that we are talking about, right. So there is a job that comes here, right, that goes to these two queues, right. So systems, right, this is your arrival. Whenever a job finishes, always comes with this CPU disk, right, this is your CPU, this is disk, this is also disk, right, A, this is disk A and disk B. Okay. So we are now assuming that a process comes in, requests the CPU whatever some number of times, it runs sometimes on the CPU, then it goes to the one of the two disks, then it comes back, there is no self loop here, right. So this is requested here, then I go to this disk A, I come back and process in the CPU, then I go to disk B and so on, right. So if I am telling you that now I have not defined this is my inline, right, then from here I also have, so these are the two options, I will also have an outline, out looks pretty bad, right, this is the outline. So if I know that there are 5 jobs, right, in this observation period that have left the system, and if I know that every job requested will request disk A 6 times and disk B 8 times, right. So when I started the system there was nothing in the system, when I am finishing the system observation period, that is, right, there is nothing in the system. So if 5 jobs have left the system, that means that this same each job must have come to this disk 6 times, right. So therefore the number of completions, right, so the number of completions of this is simply 30 and CB is 40, right, that's what this is trying to tell you. So the number of completions that each device sees is simply proportional to the total number of completions and the visit ratio for that particular device. Okay. So even if there are small numbers, I mean, because we are mostly looking for performance trends, right, we can safely ignore that and say that okay, this is one sort of regeneration period where I started with some nothing and then ended up with nothing again, right. So therefore visit ratio is Ci by C. So where this law is useful is I can sometimes simply measure the number of completions, right, at each queue, that I can simply sit and watch. I have networks of queues, I can measure the completions at device I can measure the overall number of completions leaving the system, therefore I know that the number of visits to this particular device has to be this much, again as a mean, right, therefore the mean number of visits to this device is simply this by that. That's it's not that every job, we are just assuming that every job makes that Vi visits, right. It's possible that let us say 5 of you have to go to the DR's office, the AR's or AR DR and then register for some signature, and they keep you in a loop, right. You go from this, you go to the DR, then you come back to the DR again, right, some several loops you do, then you just sit and measure the number of times students leaving this DR's office, that is the total number of requests made to that device, and then only 10 of you are there that finally leaves the admin building, right, that is your CNAM. So you know that each of you has to spend, even though possible that one student might have gone twice, some other student might have gone 8 times and so on, we are simply counting the total number of requests made to that particular system and using that as a mean approximation, as a mean only we are looking at this stage. Okay. So that is your so called force flow law.
Yeah, so the C0 Vi need not be the value that comes.
Yeah, it could be also from the past jobs that are there in the system, but then the assumption is that some of these guys also got stuck in the same queues, right? Right. So what it is okay. So what? So for example, let's say there are 2 customers already in the system, right? And then you had 8 customers coming in, and then in the time period that you are observing, these original 2 guys also left, and 6 of these new arrivals also have left, right? So if you take that as a very, so these are all sort of very gross assumptions, right? To give us just some sort of indication of the performance itself. Right? So with this now, okay, we can derive a couple of other laws. Okay, so the system throughput x, right, is defined as Ci by T, right? So this is a system throughput. So therefore, the device throughput did I say Ci? Sorry, C naught. Okay, this is the overall system throughput, which is CO or C naught, whichever it is. And this is simply, this is again by definition, right? Ci by T, this is what we had defined earlier on, which is nothing but so Xi equals so again where this is useful is once I figure out system throughput, I can actually figure out the device throughput because I know the corresponding visit ratios. So we will see examples of where this will be used. Right now it is just just pouring out these derivations. So usually what will happen is you can measure some parts of the system, and from that you can make some derivations in terms of the overall waiting time and things like that. Okay, and then next we have our u equals xi si, right, uxs rule. This I can rewrite now because of this new derivation as, so xi is nothing but x into vi or vi into x, however you want to look at it, right. Now I can combine this vi into si. What does vi into si actually represent?
It is total time actually, sir. Means number of visits and mean service time for
mean
device.
visit time.
It will be mean. It will give
I
total.
have to change the tape, so I have to wait.
Okay. It will give, sir, total.
So okay, I will answer, then we will come back and answer this again. Yeah. So tape, you want to change?
It will give total time at that device.
Mean.
Yeah, total demand on the device, right? So called demand, the amount of time that the the total number of visits to that device vi into the total number of
Mean service time.
The total time in the device. Total time in the device.
so VISI, come back to VISI, come back to NS2. So VISI is simply the demand made by a given job on a device I. So this is represented as x into di, where right di is the number of visits made by a given job to device I and the service time for each visit. So this is so called demand, right. So this is the unit of this is in is time, right, this is a demand time. Okay. So this is another rule that again when necessary, sometimes you know x, sometimes you know di, depending on what you measure, right, and then you can compute ui based on that and so on. Okay. And this di is actually important in systems because ultimately what you want when you are trying to conduct performance study of a system, then you look at the di across all the devices. you will find that there is always one bottleneck device, right. The device with the highest DI is the so called bottleneck device. So when you want to redesign a system for improved performance, you will try to go and attack this device with the highest DI and then somehow reduce its delay time, right, reduce the demand on that particular device. So reduce the demand is to make the device faster, right. You can cut down SI, for example. SI can be reduced by making the device faster, either a faster disk or a faster link or something like that, so that you bring down your the bottleneck in the system, because if you will later on we will see how this is, right, will DI will essentially impact your overall performance of the system. It will be DI will it will be something N by D plus Z and so on, we will see. Okay. So the device with the highest demand is the so called bottleneck device. Okay. So to go back to your question on NS2, no, NS2 you do not get to see the internals as clearly as this. Very high level TCL scripting is what that you are doing. So, so yeah, this is an interface that I wanted people to look at other than NS2, right, because it is more generic. Not everybody here will ever work in networks tomorrow, they will work in something else. So you should be able to build a discrete event simulation system for any other system, not just networks. Okay.
Sir, in this case, when you say bottleneck, right, you're just trying to actually reduce the amount of time by reducing the service time, but not the number of visits. So it's not kind of a load balancing system, right? So where you see.
Yeah, it is not enough, because the number of visits depends upon the jobs, right, what it is going to do. If it is going to have several disk writes and discretes and so on, that is something that you cannot control from the system perspective, right. You have a job with a particular behavior, and the only thing you can do in the system to improve performance is to give faster devices that will essentially bring down your SI, right. So that is what you want. If you want to say which of these devices is a bottleneck, right, then you should try to make that faster. So if you go to the bank, for example, right, if the printer is always a bottleneck, then you know that the printer is slow. Everything else you get process to process, then you go to the bank and then you should wait for a DD, and that takes forever to print, then that is where your bottleneck is. So you would say, okay, I know that this device has to be made faster if I want to increase the overall throughput of the system, otherwise people get stuck at that bottleneck. It is the same thing here. Bottleneck device would be the place where a lot of jobs queue up, and therefore you end up having longer queuing delays because of that. Okay. Okay. Now for some numbers. Okay. So we have, there is a time sharing system. And like any system, you always have one, right, on logging. So you look at the accounting log and you get some information from this accounting log. Okay. So this is a system with a CPU, there is a disk A and B, the standard example that we have seen so far. So these are all the components of the system. Every job gets submitted to the CPU, but it goes to the disk several times before it finally completes and leaves the system. Okay. So there are some things that we have measured. So each program requires 5 seconds of CPU time. Okay. Then some other measurements we made. It makes 80 IO requests to disk A, 100 disk B. 80 requests to disk A, 100 to disk B. Okay. Then by measurement we have found that disk A takes 50 milliseconds per request. So we just have timed the disk, and the disk B requires only 30 milliseconds per request. Now in this system it is like an old fashioned time sharing system where there are terminals which are connected to the CPUs and so on, and so there are 17 terminals, normally n terminals. Right now there are 17 terminals which are recycling these jobs, right. So terminal, the basic operation of this time sharing system is each terminal generates a job, right, and then it gets processed in the CPU, it comes back with the result, and the terminal goes into think state for some period of time, then it again regenerates. So right now let us not look at think state, just that there are 17 terminals, we will see how that is useful, right. There are 17 terminals in this connected to this computer, right. So there are 17 essentially active users that generate jobs to the system, and the throughput of disk A, right. So we have from the logs again calculate the throughput of disk A is 15.7 jobs per second. So these are all the measured parameters, measured values from your system. So ultimately I want to find out the utilization of all the devices in the system first, delay comes later. Just say I want to find out the utilization. Ideally I want to see what is the total delay, right, total throughput and per delay, per device throughput or per device delay, okay. So let us just try to find out the utilization of each of these three, CPU, disk A and disk B. So how do we proceed? What do we know? What is it that we need to find out? So we know VA, right. So let us so we know XA, which is the throughput of this particular one device, right. Alright. So we know the visit count. What is the visit count of A? 80. Visit count of B is 100. Visit count of CPU is how many times? So 80 and 100 is given to us. So how many times job? 180 plus 1, because you have one final execution where you do not go to the device and finally leave, right. So each job comes, runs on the CPU, goes to disk A, comes back, runs on the CPU, goes to disk A or B and so on, right. So vCPU equals VA plus VB, and finally there is one execution where you simply say exit, you do not go to either device. So there is always the last quantum of execution, so that you have plus 1. So every time you went to VA or VB you had to go to A or B, you had to go to the CPU, so therefore vCPU is 181. Then we know the demand. So what is that, 5 seconds? That is your dCPU, right. We have measured and founded the CPUs, right. Each job required 5 seconds of CPU time, that is what something that we measured. So dCPU we know, and SA and SB also we know, yeah, okay. So we have D, so from D let us try to find out other things. So what will be the utilization of the disk? This is simply SA into VA, right. We know both parameters, so I know that the DA is very easy. So again this is just these are just routine computations, right. So SA is 0.05 seconds into 80. So this is 4 seconds. So we know that XA equals 15.7, right. Now which I need to find the system throughput. So let us say I want to find out X, that simply XA by VA, right. So the actual throughput of the system is just 0.1963 jobs per second. Okay. Now I want to get the U value, right, the utilization for this. So U is dependent on U equals XS, S I know, right. Do we know SCPU? We know SA and SB. What is SCPU? How do you get the SCPU? The service time. Right. You know DCPU, you know vCPU, right. So SCPU simply DCPU by vCPU, which happens to be 5 by 181. What is that? Okay, so we will figure it out. So now that I know the overall system throughput, right, this is X into vCPU, right. So that is nothing but 0.1963 into 181, so that is 35. So the throughput of the CPU is basically 35 jobs per second, right. This is what the CPU can handle. Then we can compute the throughput of this disk B, which is again X into VB, so that will be 19.63. So you can write a very small program to do this. Only thing is you have to know, so there will be some terms missing, right. So you need something like a symbolic program that says, like in MATLAB, right, solve this comma, right, give you something is X, something is not given, and then you will simply spit out what the values of X are, right. Some known, some unknowns, and somehow magically you figure out from one from the other, right. So the better way is to start with, okay, we say utilization start with U equals XS, so we need to find out X. So actually I am working this from bottom up, should go the other way. You know the S in this case, in some cases we won't know the S, it will be sort of hidden in some other value, right. So you have to find out X. So to get the X I need to know the throughput of the system. So therefore I know throughput for one device, I can calculate the throughput for the entire system and then kind of work backwards from that, right. So so now my X's, and then what are the utilization values? So this is X CPU into, and this we computed as 30.48. Oh, sorry. X, no, sorry. It's just X. UCPU is actually X into D, right? It is X into XS. Right. So if I had, but this is simply X into D CPU is your UC. So that means that your CPU is utilized to the fullest. Now you look at your UA, which is 0.19, I guess. So we had computed earlier DA to be 4, right. So this is 78.4, UB equals okay. So this is the status of your system. So what is the big deal with all of this, right. So at the end of this, so you have taken some measurements from your log, you are now post facto computing what were the device utilizations and so on, right. So as system designer you are supposed to look at this and say, you know what, my disks A and B are okay, or A is actually reasonably utilized, 80% utilization is fine, but the CPU is heavily utilized, 98%. So which means that the queuing time at the CPU is going to be fairly large because it is operating very close to capacity. CPU is always busy and therefore jobs queued up will end up requiring, right, will end up having higher delays because of the fact that the CPU is heavily utilized, right. And disk B is actually underutilized. 60% utilization is probably not worth it. You have paid some few $1,000,000 for the disk those days, not now. Then you are not, the disk is not getting utilized that much. So we can't do much of course because the disk utilization depends upon the way the jobs are running and how often they read and write from disk, right. So you now go back and say, well, I have this, so which is the highest D here? Highest D is for the CPU, right, of these three. So the CPU is the bottleneck. So you will have to somehow speed up your CPU, bring in a faster CPU to cut down the service time of that CPU, and that thereby bring down the demand and then bring down your overall throughput, sort of delay in the system too. Okay. Right, because the number of jobs finishing per second is very small, relative to whatever that is, but okay. So we never really use that 17 here. We will use that in a later thing, but it will come later on. But whether the 17 terminals, right, we are not really looked at. Questions on this example? So only two rules that we really needed. One is two or three, right? One is that forced flow, which tells you given V, given C naught, how do you get the corresponding visit values, and vice versa. And then U equals XS, right? And then the fact that D equals S into V into S. So these are all the three things that we need. Questions? So another way of representing this visit ratios is also as probabilities, right, which is what we have been doing so far. We have always used this, right, when we did the first Markov chain 2, there is a CPU and there is a probability, right, of going to this disk, it is a probability of going to this disk, and then there is also a probability of, right, coming back. You have seen all these things where the three probabilities should sum up, so it should sum up to 1, right. There we looked at it in terms of states, now I am looking in terms of queues with packets, and I move between queues from one part of the system to another part of the system, right. So we can specify it this way too, and essentially your you can equate the visit ratios and these probabilities. So if one or the other is known, you can compute the other one. Okay. So let's see. I'll just put this down. We can come back and visit this because of slight digression here. We can equate the visit ratios and the transit. And the next law is Little's law. Okay. So then at the ith device, the queue length. So now we are getting into delay. So far we did not look at delay. So queue length and the response time where the queue length also includes the one that is in service, right. Response time is like we saw before, the total delay that each customer sees at a particular device. These are EFT that is your response time that we saw before, right, or is it, what did you use, yeah, EFT. So QI equals lambda Ri, right, or lambda I Ri. So lambda I is the number of arrivals to that device. So we know this from before, right, EFN equals lambda into EFT. So then if the job flow is balanced, then lambda I equals xi. Remember this was the assumption we made, right, AI equals Ci. So in terms of rates it is simply lambda I equals xi, so then Qi equals xi into Ri. So again to remind you, this is the number of jobs in device I including the one end service. Did you get that? Okay, so that's we know queuing. Next is our so called response time law. So fourth law in the sequence. Okay, so if Q is the total number of jobs in the system, X is the system throughput, we know that from before, and R is the system response time. So this is the actual time taken for a given job as it goes through the entire system. So what is the relation that ties these three with Little's law? Q equals XR, right? So that's not. And Q is also, so the number of jobs in the system is simply the number of jobs that are queued at the, we have m devices, right. So devices are numbered 1 to m, there are m devices and simply the number of jobs queued up in each of these. It is not possible for a job to have one leg here and one leg in some other queue, so neither one queue or the other. Okay. So this I can now expand with Little's law, right. So if I divide everything by, now I basically want to find out the overall system response time. I can find out the individual queue response time and then I want to compute the R is what I am looking to find out, right. So to get R, if I simply divide by X on both sides, then you will end up with right. This is again very straightforward. So what is x1 by x? X1 is the number of visits, total number of visits to make this particular queue. This is your V1, right. So again you can simply derive this without, it simply says that if I visit each device x number of times or v number of times, then that into the response time plus blah blah blah, right. And this of course this is where those independents our closed form, this is where the closed form comes in, where I am independently analyzing these, then I am simply adding them up to get my overall response time, right. This lets me, that closed form solution lets me use this, even though it is intuitive, to actually show that this will work you need that closed form property. So this is your overall system response time. So now we can proceed further, right. So we last time saw utilization, from utilization then we can get throughput, now we can slowly start building up the, so now we finally can get the response time of a job that is sitting in the system and how we can do that. So this is your general response time law. So if I give you the R's and the V's, you can simply compute the actual value, right. Okay. So now there is the special case called the interactive system response. So this interactive system has this CPU plus disk and all that in queues. So it is like a circulating system. So you have a set of terminals. So these are terminals. We will just assume that they are numbered 1, 2 up to n. So basically terminals, interactive system will, right, you submit a job to the system, let us say ls, it is what you submit in the olden days, and then goes to the CPU, gets executed, you get back the response, and then you have to, then there is a think time before you issue the next command, right. So there is this notion of think time between time think time. Okay. So each user cycles, right, so each user generates a job which takes R time for service, then it's Z time for thinking. So in a period T, right, so the cycle time for a user is R plus Z, right. This is to handle a request from the system, then the next is to think before you submit the next request. So the number of jobs per user this is submitted, right. In time t is simply t by r by z, right. So total jobs submitted because there are n terminals So this is a closed queuing system, right. So now the system throughput. So we are trying to find out R, right. So that is where we are now heading to. So what is the system throughput? Is simply the number of jobs submitted. Again, it is a flow balance system. So this is the total number of submissions divided by the total observation time. Therefore, x equals n by r plus z. N by x minus z. This is your interactive system response time. So in the previous example that we saw, right, in the earlier example, I said n was 17, right. Now that is going to get used. N was 17. Let us say z equals 18 seconds, and we computed x to be 0.1963, right, jobs per second. Therefore, R in this case is simply so we will do one more and then only bottleneck analysis remains. Okay. So we won't go to bottleneck analysis before the quiz, we will just finish off with the same. So continuing with the example, so we had computed x CPU to be 35.48 and all that, right. So this was the throughput of these various devices in the previous example, right. So let the measured, right, queue lengths, average queue lengths, I will separate this Q CPU. So the CPU had 8.88 jobs, so these are now measured, which we can just take time snaps, look at each of the queues and then compute the average queue length, right. So this is the average queue length that is given. So we have x, we have q, therefore we can find out r, right. So given that q equals xr, right, this is the rule that we used before, right, qi equals xi ri. So therefore r, so the response time that is in the CPU is simply 8.88 divided by 35.48. So that is 0.25 seconds. Likewise, RA you can compute as just giving you the values, but you can compute the others, right. RA is simply 3.19 divided by 15.70 and so on. So once I get the R's, now I can actually compute the overall response time also differently. We did it one way, I can do it another way, right. So this is equal to VI RI. So that is nothing but 0.25 to 181 plus 0.203. I must warn you on one thing, in this book now and then they have examples that have incorrect calculations. In my older version I used to have made all those changes, but some of those, so you have to go back and check if indeed it is 0.203 and so on. So always check. In this particular case it is correct, but there are many other cases where they have. So this is